All right, it's kind of cool. This will be front axle failure for Honda Civic. So I watched this guy over here, South. So if you guys want to find his video, South Main Auto Repair. I enjoy South Main Auto Repair. Enjoy watching his channel grow also. So he had a front axle. This shows that he had a front axle issue. This is the replacement. And I'm going to skip through here and I'm going to show you what really happened. He's not sure. He's never seen one before. So I'm going to do this video and then share it to him and explain to him what happened or what he's looking at. There's the damaged axle. I'll fast forward it.
One on the driver's side, there was none here, and both the holes are completely open. Well, we're taking the Mrs. O out there.
His wife shows up in the videos
Oh, it's on your head.
also, and that's who he's going to be talking to. She's not the customer. And they're much more, usually more pleasant than this. He's, just getting his ass handed to him a little bit here. But here we go. But it's not really handed to him.
Give her the beans. You're pushing over on this stuff.
In other words, if you watch the video, don't base his character on that, his shortness this time. He's not really that short. He's pretty cool. They're both cool. They interact well together. Okay, so he's going to just remove the lower arm.
Slip it in right underneath the boot.
But what's important here is this is the broken part right here. It's got a very interesting part about this fatigue that I'd like to explain to you, and what my theory goes on why it broke here based on that bushing. Notice that bushing he's going to talk about in a second. Well, he doesn't know what he's talking. He does not know what I'm going to reference, but it's not resting on anything. This bushing is not. That bar appears to not be resting either. Of course, it should not be.
Here is to not ruin the boot. That's what we're hoping to achieve.
So there's a better shot of the two ends. This is the broken end here, the fractured end.
15/16. We'll just use this little ratchet here. Oops.
I'm gonna scrub forward, so you can see it's pretty secure still in the hubs, both ends.
Let's see.
On this side, you can even see there's some looks like rubber inside that side also. We'll go for it.
And it did not damage the threads. No.
Hey, Zelix.
Technically.
Hey, Tom.
There it is.
All right, so hold on.
There's that.
Right there. I want you to, there's that piece there. He's going to throw it on the floor, but let's back it up. This is what a fatigue fracture looks like. There's no rotation. There's no torque on this. I've got to get it to. Yeah, it is tough, right? Next piece. He's going to be a little better view of the next piece.
See if you get the rest of the axle out. Yeah, there's a lot of rust. Is the axle designed like that? You see the
perfect. Couldn't ask for better than that. So he showed it from this side, and you break this. I call it the table. It's actually called something else, but I always think of it as a table and the lip. That's your fracture. Your fracture begins here, all the way down to here. And then it's just the last bit to just knock it off. And I'll show you now. Let's see here. Metal fatigue. I set up a video, lined up a video for you for that. Those fractures you saw there, it looks like this. This is the fracture. This fracture here. This is your metal fatigue fractures. These are your metal fatigue fractures. It's metal fatigue fractures again. Now let's go ahead. So what he did, this video did, the tester took structural steel, and the steel is too large to be able to test in the machine. It's limited.
In a well-defined manner, suitable.
So they basically machined it down, put these knobs on it, these ends on it for being able to hold it in place while they do the testing. The testing, therefore, what they're going to test is right about here, about a quarter inch approximately.
Suitable specimens have to be machined from the rods. This specimen type would be ideal. The shoulder-shaped ends have been designed for safe gripping. The actually tested region is cylindrical with a diameter of 6 millimeters.
Jumping
Together
on.
with two.
So now this is how they secure it in the machine. And the machine will be explained, so he'll do it better than I can, although I can give you clarity on it. So this is just anchored in. These ends are just to hold it in place because a force is going to be applied, pulling it apart and then releasing that force. This is what it ultimately what it comes down to. Applying, releasing. If I could do that, say 2 times a minute, well, basically my frequency will be 2 times a minute, the cycle. This is going to be 25 times per second is what they're going to cycle this at, changing the weights, the amount of force, very limited force. But here we go. And you'll see the failure of this beautiful seal and the non-failure of it.
2 half shells, he inserts one end of the specimen into the right specimen grip. With a union nut, he locks the right end. The preparation is now complete. Alternately, with a tensile force of 7 kilonewtons and a compressive force of 7 kilonewtons, the mean force is 0.
So what does he mean by mean force in those two? One is applying a tension, a pulling, and then there's then it goes back with the 7,000 compressive force, with 0 being the center line, always coming to 0. That's your mean.
A click on the start button and the testing machine begins to stress the specimen periodically.
So here's your tension, pulling away, putting it back in, away, back in. This is the side that's doing the work there. This is stationary. This front part is stationary. This is the side that will be doing the tension and compression. This side will be doing the frequency.
Our fatigue testing machine is equipped with a mechanical resonance drive.
Oh, perfect. So that's the part that's going to do the compression in and out to 0, in, out. These 100% going equally. This secures it. This adds the resonance. What he's going to say is basically it's redirecting all the vibration down here, the resonance, to back and forth cycling. That's here on this piece of material.
The specimen is connected at its left grip via a load cell to the machine frame. At the right,
that's the machine frame, saying it will be, well, I guess it's here too.
Right grip.
No, it'll be back there. What am I saying?
A spring is mounted, and there in turn a mass. An imbalance stimulates the mass to vibrate.
That's your frequency.
Longitudinal guides prevent the mass from vibrating in the transverse direction.
So redirecting the forces down the specimen.
Via the spring, the test force acts on the specimen.
So it goes to 0.
By varying the excitation frequency of the imbalance, the test force can be controlled. In our case, the specimen is loaded with about 25 cycles per second.
Now let's go.
Meanwhile, the first specimen has already endured over 300,000 load cycles and
300,000 load cycles. Now I'm going to zoom in because I want you to watch the beginning of a stress fracture. And this is what you look at airplanes, everything on to keep track of this stuff. But here we go.
still seems to be intact.
Right there. There's the beginning of it, right here.
In reality, however, several cracks have already developed starting from the surface, the so-called fatigue cracks.
See
With
it?
each load cycle, they grow a bit further into the specimen. The biggest crack gains the upper hand, grows the fastest, and
So there's your fatigue crack. Notice it was secure on each end, but the vibration came down, the frequency. And this frequency, I'm really in love with frequency, guys. You can do so much for it with frequency. If I change the frequency of my voice, I could hurt you, you would not like it. Or I could be pleasing to some people. It's just frequency. I want to show you, we'll get to that. I want to show you the force is only 1,406 pounds. I want to show you the stress strain curve. No, I think that would be too boring for you. Yeah, this is what it, another boring one for you, I think, trying to explain it that way. So with that, to not bore you, I then go to Google. I researched some video images I could find. And so what you saw is that first crack was right there. Based on that frequency, it's done. It created that. It created this table, I call it, and it's not called a table. They call it, it's rarely referenced to as a, so again, there's your fractures. You don't see any bending. This is what's so indicative of why it's a stress fracture. You won't see bending or necking. You'll just see necking where it's elongating, the material's elongating. You just see, bam, you just see this instant break. And that's what he was looking at, that he thought was rust and everything else. And you often find a clean surface. These are microscopic images of the surface to help other people find and visualize what they're looking at when they're testing. Fatigue slow fracture zone, instantaneous fracture zone down here. So instantaneous, you see that's that lip. That's that lip you see here, this part. Now let's hit the video and you'll see it. And it will go back.
And finally leads to fracture.
There we go. There's your lip. There's your married family side of it, your mirrored family side of it, your married.
Fracture after 381,000 load cycles.
381,000 load cycles. Now, I'm going to fast forward this because I want you to understand that cycles
The first
matter.
test is finished. The material tester removes the fragments cautiously and inspects the fractures, reveals two regions, the rather dull, predominantly flat fatigue crack propagation area and the rough residual fracture area. The residual fracture area results from the final catastrophic rupture. The fatigue crack propagation area has developed during the cyclic growth of the fatigue cracks,
Cyclic growth, frequency.
starting at the surface of the specimen.
So we go to your car here. Where do you get your frequency from? The spinning of the motor, also the spinning of the tires, sending frequency down that rod, that shaft. The rod itself spinning also, because that is a drive shaft, right? That is not a drive, is it? No. Was it? It doesn't really matter for this one. I don't know. It's a drive shaft. If you guys know, tell me real quick. I didn't really think about that. It doesn't matter. It would be under torque then. I don't think it's a drive shaft. Let me think about that. I'd have to see his video again.
What does the
I got too caught up on the fatigue crack.
fatigue crack propagation area look like at higher magnification?
This one you'll find boring,
One
I
of the
think.
a typical phenomenon.
Short striations.
Of course, now we want to know how many load cycles this material can endure with other loads.
So there are other
For
test
this
samples.
purpose, the
Other test samples.
material tester picks the next specimen from his supply and installs it into the fatigue testing machine.
Remember the last one fell, they what, 380,000, 300,000, 380, something like
He
that?
chooses a higher alternating load for the second specimen, a tensile force of 7.5 kilonewtons.
So he went with 7.5 kilonewtons. Is that on my scale? So maybe he stuck with 7.5. He's got like 1,600 pounds on it. And same cycle, 25 per second.
And a compressive force of 7.5 kilonewtons. Under the increased load, the specimen is only able to withstand 43,600 cycles to fail.
So he added, so all he did, it was 6.5. That's what it was. He went to 7.5, and now it fell at 47,000 cycles as opposed to 380, I think it was, right? Something about that. You have to look at the video again. All he did was out added 200 pounds, 200 plus pounds, and now all of a sudden can only do 47. So that little bit of weight counts. Now let's go on. Tire pressure could really help with this too, believe it or not. Changes the frequency, vibrations from the road.
The third specimen is only tested with a cyclic load
Of course, balancing your tires helps.
of 6.5 kilonewtons. Under this reduced load, it does not break even.
Oh, got that wrong. This is the 6.5 kilo one. This one goes up to friggin' major number.
After 3 million load cycles.
So that's what it was. You dropped down 200. So correction to my video. You dropped down 200 pounds and now you're at 3 million. Went from 380 to 3 million.
Additional specimens complete the series of measurements.
What did he put it at?
End of the specimen into the left specimen grip and
7,000.
nuts.
Oh, he put it at 7,000
He intends
kilos?
to load the first specimen alternately with a tensile force of 7 kilonewtons.
Okay, he did 7 on that one. So 6.5 got you 1 million, 3 million, whatever the hell it was. And 7.0 gets you 15,736 pounds. 70, I'm like, what the hell's wrong with that? Yeah, 1,573 pounds, just that little bit. So if you were going to spec this, for example, you might say, okay, we get 3 million. So let's use that and call it a life cycle of half-life, 15, 1.5 million cycles. Or change the metal and test it properly. Don't scale it down like that. That's using extrapolation, and I hate that for engineering. Extrapolation is probably one of the worst things you can do for calculations in engineering. And all the failures can prove that to you. And this is your stress fracture in the human body with jumping jacks, etc. I have those before. Here is a fatigue fracture of, I don't know what that is. It's obviously a piece of metal. I don't want to bore you with the scales. There's your plateau. I call it the table. And that's why I call it table, plateau. All right, so now you know what the stress fracture looks like. And let's go to back to this. That's what it looks like. So what's interesting here, though, is he's going to talk about this boot next. But take note of this taper. If this pipe was fully this way, you would call it necking. But I think they designed this to have, I don't think it necked at all, because this is restrained, if you will, by the lower arm and also the location there. So there is no ability to stretch this to cause that tension in this bar.
See the taper to it?
And he thinks it might be rust, but it's not. Rust doesn't do that.
Or did it just rust and whittle away till it got to a point?
See, so you'd have to grab a new one of these. Also, with that bar, that rubber boot now, don't make light of it, but that rubber boot, if it appeared to be snug, but if that rubber boot was somehow pinned and you started spinning this bar, it would give you some type of wear, but I don't think it did, because what would it do? Polish it. It would be polished, not of this look. So this one, I would have to find out what original one looks like. Did they taper it, and why the hell did they do that? Obviously, they thought they were handling the resonance, but let's go back.
That is the question, because we look inside this rubber.
And this is all rubber. His hands on the outside is rubber too, after evaluating the video 1 million times. And I hope he responds to it. This appears also to be rubber, but 2 layers of rubber and rubber. Now, rubber is not going to cause a rusting effect, unless it's got some metal inside of it, oxidation, but go ahead.
And you see all the rust that's in there.
That is interesting, the rust. He is talking about metal that's on there. So you get a fracture. So watch how I work on that rust. So you get a fracture. After you have the fracture, it's no longer connected. Then you can introduce the metal frequency still bouncing around, and then you can get some further erosion based on all this other crap still sticking in there, participating now, being isolated, being confined with the rubber. It is interesting, though, that the perfect taper of that damn thing. I just don't imagine this damn. I don't imagine that taper. It just got me. And I looked at this new one that he installed. It's an aftermarket, but I don't have anything in my files in my brain that says why taper. So I have to. That's the one I find fascinating about this. But I trust that he's pushing off metal because he says he is. So it delaminated, I think, after the fracture. But it's still the same materials. So I'd have to say it was like sometimes still electrolysis happening as this thing is spinning. Maybe some static was created, but then rubbers are ground. It's just that I find amazing, and it's perfectly tapered. Not perfectly, it's evenly, consistently tapered. Nevertheless, it's still a stress fracture no matter what. But this metal one is this other metal deterioration is related to this rubber being at that location, or the machining from the factory tapering it off on purpose. Again, it's not necking, where you stretch a material and it becomes necked or thinned. The backside is what is like a tell for me that he's saying it's rubber, but it's no